Yeah, I included a notebook with the quantum circuits and Bell states lecture. It's your quantum hello world. It goes over the basics of how to use the hardware, and it gives you set up a GHZ state, which is kind of a specialized Bell state that we'll be talking about today in today's lecture. All right, hey, it's 9:30. I think we're gonna get started. I'm going to be going through the presentation. If there's any issues or if anybody has a pressing question, you please feel free to unmute yourself and ask a question. Um, but I'll be looking at my presentation, so I can't see the Discord chat. So, quantum circuits 101. Yesterday we gave the barest bones of what a quantum circuit and a qubit is. Today, what we're hoping to do is to explore how we actually control these quantum circuits to enact the algorithms that we want to do. All right, as a quick refresher that, with a classical bit, it's either 0 or 1, but a qubit is in the state 0, 1, or both. And you'll notice we have these funny little brackets around the qubit. That's because we're actually representing a vector where it's 1, 0 or 0, 1. The number in the bracket indicates at which position in that bit string the qubit's at. We can dive more into that later, but for now it's enough to call the qubits in state 0 or 1. Now, even though they can exist in superposition on the measurement, they collapse to 0 or 1. So quantum gates are the building blocks of quantum circuits. They work like logic gates in classical computing, but quantum. And in quantum, there's quite a few more degrees of freedom than exist with more traditional classical bits. And there's two primary types of gates that we're going to be talking about. There are single qubit gates that act on one qubit. The most common of these is the H, X, Y, and Z. In many diagrams, you'll see that plus symbol to represent the X gate. It has a very similar behavior to a NOT. And then we have multi-qubit gates. These provide entangling behavior between gates. Down here I have a controlled NOT, a swap, and a controlled Z gate. These are what provide that entangling behavior and are how we accomplish much of what we're doing. But first, we've seen this little sphere over here on the left-hand side several times throughout our lessons so far. But we need to talk about what this is. This is called a block sphere. The block sphere is a representation of a qubit. A qubit can be thought of being a vector of length 1 that is pointing to some point on the sphere. So 0 is the North Pole, 1 is the South Pole, but also we can do rotations between North and South. So we have 3 axes that we're working with here, the X, Y, and Z axis. And that's what those X, Y, and Z gates act on. They rotate about that axis. So we are able to represent the state of a single qubit as this length 1 vector, pointing to some point on the sphere. Now, as you increase the number of qubits, this visualization becomes much more difficult to work with. However, it's still very useful for getting an intuition on what you're doing with these gates as you work with a qubit. Let's talk about some basic single qubit gates. The X gate flips a state from 0 to 1. it does a pi rotation around the x-axis in that sphere. Now the Hadamard creates a superposition. It takes the gate from a state of 0 to a state that is half 0 and half 1. It takes it from that north pole to lie on the equator. All right. Now Z gates rotate around, the Z-axis, which can be thought of as a line going from the north pole to the south pole. This is how we are applying interference between qubits. If we have two qubits that are entangled and we do a Z rotation, we can have that constructive and destructive interference that allows us to quickly evaluate the item that we're looking for without iterating through individually. We increase the phase of whatever we're looking for. So the X gate, we have this block sphere representation here, where if we apply an X gate to a qubit, it takes it from pointing at the north pole to pointing at the south pole, where that Ket1 state is. This is, a very fundamental gate. Oftentimes, as you're encoding things, perhaps you're trying to encode something as a bit string, you'll just iterate through your qubits applying X gates so that your quantum circuit represents the state 00101, or whatever the case is. The Hadamard gate. So here we're starting at that south pole, but it does that pi/2 rotation to where the qubit is pointing at somewhere at the equator. And this is what we mean when we say that it's an equal superposition. That's an understanding where the qubit is, but you need to remember that whenever you measure this, that state will either measure as 0 or 1. But since it's pointing at the equator, it collapses to 0 and it collapses to 1 about 50% of the time each. Now this Z gate does rotations around that Z-axis, does rotations along the equator around the around the Z-axis. So we have these 3 degrees of freedom that we are working with a any individual qubit. So a little bit about like running and visualizing in Qiskit. I'm going to be including these little short code snippets, just that way we get familiar with seeing it, and also that way we can see that it's relatively straightforward. All right, here I did some imports where I imported a simulator instead of running this very basic circuit on real hardware, and some visualizations to plot the histogram. I'll talk a little bit more about that in a second. But I initialize my quantum circuit such that it has 1 quantum bit and 1 classical bit. We need something to measure to, so we have to specify classical bits for the measurements. I apply a Hadamard gate on the only qubit that's in this circuit, since I only have 1 qubit. That puts it on that equator, and then I measure from my 1 quantum bit to my 1 classical bit. I specify my simulator, and I say to run this 128 times, see what happens. All right. I get my result and the counts of how many times it came out 0 and how many times it comes out 1, and I plot this histogram. And so with only 128 shots, it came out as 62 and 66. Now, remember, we're dealing with probabilities here. So as we increase this number of counts, it would trend closer and closer to true 50%. But just like you could flip a coin 100 times, and you wouldn't necessarily always get exactly 50-50. But as you increase the number of samples, it will tend more towards that actual probability. Now, multi-qubit gates, the controlled NOT gate. The controlled NOT gate provides entanglement between 2 qubits. What it allows you to do is to have information propagate throughout a quantum circuit. So in this little example here, I made a quantum circuit with 2 qubits. I placed an X on qubit 0, and then I placed a controlled NOT from 0 to 1. So all qubits always start in the 0 state. I flipped it to the 1 state, and then I did what's called a controlled NOT. I say that like if qubit 0 is 0, do nothing. If qubit 0 is 1, flip the state of qubit 1. And so we see that whenever we run this, we end up with state 1-1 100% of the time. All right. That's a very basic example of the use of the controlled knot state, and we have entanglement going on between those two qubits. Now, a Bell state. A Bell state is a specific state where we have these two qubits entangled in such a way, so that they either both flip or they both don't. So in the previous example, I had an X on qubit 0 where I placed in 1. Here, I placed a Hadamard or H gate on qubit 0, where I moved it from pointing at that north pole to a point on the equator, such that anytime we measure it, 50% of the time it'll go to 0, and 50% of the time it'll go to 1. Then I apply this controlled knot from qubit 0 to qubit 1. The controlled knot still has the same behavior, but we don't know how this is going to work out until we apply a measurement. If we measure this and it comes out 0, so will qubit 1. If we measure this and it comes out 1, so will qubit 1. So this provides this entanglement that these two states are tied together. And once we have these states tied together like this, we can later use things like interference and further applications of entanglement and superposition. That way we can do the things that quantum computing does, where we're able to evaluate large combinatorial spaces much more quickly. Here's how you would run a Bell state in Qiskit. So similar to before, I designate a quantum circuit with 2 quantum bits and 2 classical bits. I apply that Hadamard gate on qubit 0. I apply a controlled knot from 0 to 1. And I measure from qubit 0 and 1 to classical bit 0 and 1. I set up my simulator. I run it 128 times here. And then I plot the histogram. We see that we got state 0, 0 65 times, state 1, 1 63 times, but we never got state 0, 1 or 1, 0. If I just placed a Hadamard on this, we would have got, a much more even distribution. But because these are entangled and running in that Bell state where these two qubits are connected, and if we measure qubit 0 and it's 0, so is qubit 1. Now, I'm describing one Bell state, and it's the most common Bell state we'll see, where you just apply a Hadamard and a controlled knot. All right, we can represent this as, the qubit state 0, 0 plus 1, 1, with equal probability. But, you have to realize that we're dealing with these qubits that are lying on this equator. And so we can apply various other Bell states as well, where if we add a Z gate to that, we'll have 0, 0 minus 1, 1 over 2. And so there's also this phi plus and phi minus state, different variations. You'll notice that we'll have anti-correlation in these phi states. So what that means is that if, our coin on qubit 0 is heads, then qubit 1 will be tails. It perfectly anti-correlates. Instead of them being the same, they now work oppositely. This is really important for further applications of interference whenever we are trying to evaluate these complex problems. These Bell states are foundational for quantum teleportation, the secure communication protocols. You will talk about Alice and Bob and them doing quantum teleportation. They're also really important for error correction, and we've spoken about this a little bit, where we'll have multiple physical qubits encoding one logical qubit, but having all these qubits operate in the same way once we've applied some entanglement is super important for us to understand how these qubits are operating. Another practical thing in practice is to test entanglement in quantum hardware. We'll apply these Bell states to understand the noise that's happening on our quantum hardware. And that quantum hello world has instances of these Bell states included. So circuits are recipes with qubits and gates. You set up your qubits that correspond to classical bits, but they have greater degrees of freedom. And with those greater degrees of freedom, we have more ways of controlling them. I've covered some of the most basic of the Hadamard, the X, the Y, and the Z. and then the controlled knot for our multi-qubit gates. But there's also a variety of fractional gates that are, a partial rotation in the x direction, the y direction, and the z direction. And we didn't get much into the different kinds of entanglement gates. It goes deeper, but most of the things that you're going to do in quantum circuits build on these basic tools. I want to continue stressing that Qiskit's not that hard to learn. It is a large library, but it's not hard to develop a quantum circuit, to set up a simulator, and to run experiments. Yeah, I'd be more than happy to send the Colab notebook. I'll post that in today's Quantum Circuit Bell States chat. Downloads. All right, that's in the chat now. Yeah, I'll make sure I upload the PowerPoints as well. I am going to put a delay on that. After 24 hours, I'll upload the PowerPoints, because you get situations where people think they can flip through the PowerPoint and not join the calls or watch the videos. So that way I can drive engagement. I don't have people just waiting till the end to flip through my PowerPoints. A little bit about some of the rest of the day is at 1 o'clock, we're going to be talking about the Quantum Innovation Center. The University of Missouri system, so that includes Rolla, St. Louis, Mizzou, and UMKC, are in a partnership with IBM. That partnership gives a decreased cost of access to IBM quantum computers. What that means is that, hey, everyone gets their 10 minutes free a month, but also the Mizzou Quantum Innovation Center has grants for increased quantum hardware access time and decreased cost. Right now, after your 10 minutes, I think it's $99 a minute. But I think even if you don't have a grant, you can have access to decreased costs through the Quantum Innovation Center. In September, me and several of the students from my class, they had a Quantum Innovation Day. We got to hear from speakers from IBM, like Victoria Lipinska. We had speakers from Moderna and Mr. Wade Davis, and they're solving mRNA folding problems with quantum computers. So it's they have events like that. They have a Microsoft Teams chat that is available to us for us to interact with, where they make announcements on things like internships over the summer. So that's what the 1 o'clock session will be about. And then at 2 o'clock, we're going to get into quantum error correction. Quantum error correction's super important in today's quantum computers to allow, because without error correction on any large circuit, it's just going to turn into static. Your measurements, the noise will increase to such a level that you will not be able to decipher a meaningful output at the end without some meaningful form of error mitigation or error correction. So what makes quantum computers good at handling large problems that are too complex for classical? So quantum computers have true parallelism. A classical computer, oftentimes we talk about parallelism with classical computers, but what we really mean is that we just have multiple chips and then we try to merge their results when they're done. Okay, hey, I've got 4 GPUs running, they're all checking different things, and I merge what they've done at the end. Quantum has true parallelism. That is that they are actually simultaneously checking these things on the same circuit. And not only that, because of the properties of superposition, we can make a representation of the entire state space that we're evaluating. So we can simultaneously check all possible states of this particular problem. Whenever we talk about Grover's algorithm, either tomorrow or the next day, we'll be able to talk about how whenever we're searching for an element in an array, we are able to simultaneously search that entire array while increasing the amplitude of the item that we're looking for. So what we're doing is we're actually simultaneously searching the entire space. Now, right now we're in that NISQ era, and what that causes is that, hey, if we had an infinite quantum computer, we could just knock this out, but we're still limited on qubits, so we do this mixture, these hybrid algorithms, where we're using the quantum computer to quickly accomplish math or search large portions of the space, but then we're optimizing it with classical computers. So we're handing these problems back and forth, where we use the power of quantum computer, but it's limited bandwidth, and combine that with classical computing to try to increase that capability. All right. So interlinked. What does it actually do to the quantum field? So what does it do to the quantum field? So I'm not quite sure what we mean by quantum field. So these quantum computers operate on a variety of different paradigms. IBM uses superconducting qubits, where they have these superconductors with Josephson junction that operate like a quantum particle. There's also trapped ions, photonics, and various other methods. That's largely abstracted from me as a quantum computer programmer, as a quantum algorithmicist. Um, that's largely abstracted from me. So, it's I make my circuit, and then IBM shoots lasers at something, or uses microwave pulses to control something. That's largely abstracted from me, in much the same way that a classical computer is abstracted from me. I type text on a screen, and then cool electrical stuff happens on a chip somewhere. But at the same time, um, getting this intuition of how these gates are affecting what you're doing and what we're doing with those is something that does take time. But what we're doing is we are typically encoding a problem. So we'll take qubits and we'll encode our data into this quantum circuit. And then we're trying to optimize it for some type of result. Oftentimes we're using something called an ansatz for that. So, an ansatz is a parameterized quantum circuit, where we have the quantum circuit doing calculations, and maybe we have a hybrid classical thing where we have a classical computer that is doing like gradient descent or something like that to find the best parameters for that quantum circuit. So, what's it doing to the quantum field? I don't know. IBM has a giant fridge in which they're shooting off microwaves and stuff, but at the same time, we can understand how it affects the quantum circuit and the state. But we'll be getting into that more as we get deeper into the algorithms and how all that works. Quantum useful for factoring large numbers. That is a difficult problem. So we have a quantum algorithm called Shor's algorithm that is incredibly good at factoring large numbers. The problem is we're not very good at putting large numbers onto the size of quantum computers we have today. So it's a double-edged sword. Everyone's always so terrified that quantum computers and Shor's algorithm are going to destroy RSA encryption. And I mean, eventually they will, but just right now we don't have the capacity on our quantum computers to represent these large numbers. Yeah, RSA is at risk, but it's one of those things that we've been seeing this coming for about the last 10 years. RSA is slowly being phased out. It's no longer being the default for many encryption schemes and algorithms. They are switching to algorithms that are much more resistant to quantum computing. The biggest risk I would say that exists for quantum computing and encryption isn't so much that we're going to get a quantum computer and people are going to start hacking into all our stuff. It's more the harvest now, decrypt later schemes where people are trying to, collect a bunch of data now and hoping to be able to decode it later using quantum, because hopefully by then we're using these quantum safe algorithms. Yeah, but it's I've been hearing about quantum safe algorithms for a long time. There's various different ones out there, lattice based and all kinds of things that aren't as vulnerable to the types of things that quantum computing is good at. So yes, quantum safe algorithms are definitely a research field. Now, what's most interesting, I think, with cryptography and quantum is quantum's huge capabilities for very, very secure cryptography. Quantum computing, because as we've talked about how once you measure a state, it collapses, that can be detected, and we have quantum encryption schemes such that, hey, if our communication is intercepted, we can detect that that has collapsed that measurement, while simultaneously that intercepted message is useless without the state held by the receiver. We don't get much into the quantum teleportation and the quantum communications aspect and the Kiskit Fall Fest here, largely because that's kind of outside of my domain, what I'm most familiar with. But it is a very, very intriguing field. But I think the most interesting thing about quantum and encryption isn't that quantum is going to break encryption, it's that the capabilities quantum will bring to encryption. Yeah, 100%. I mentioned this is a little bit outside my field, but on the research that I've done, we've found newer encryption algorithms that are much more secure. And it's even then, so, like, there's a quadratic speedup, which is huge, with quantum computing and breaking these prime number encryption methods. But, a quadratic speedup on an encryption method that would take 1 billion years before is still like, a very long time or very expensive. So it's going to be one of those things that, like, it's going to be a long time before it would be worth the effort, unless it was like the most pivotal and secure thing. Like, I don't think that quantum's going to be applied to decrypting things like below the like government or very large corporation level, like espionage type stuff, because while it's capable of being perhaps decrypted now, it's still a massive undertaking even with the quadratic speedup. That's why these methods were chosen in the first place, because without quantum computing the picture, it was borderline impossible, with classical computers. But, even with a quantum computer, it's still going to be expensive and take time. So I'm less sensationalist with, the quantum computers breaking encryption. Like, yes, we will be able to break. RSA is vulnerable, but at the same time, it's still an expensive endeavor, and we're finding much safer encryption algorithms that are resistant to quantum. The Majorana 1 chip. I don't know. They made very sensational claims. They published a paper saying that they've been able to not only study a Majorana state, but use it to make a useful quantum computer. It's a huge claim. The news reports surrounding it were incredibly sensational. And the paper was a little less so. I think it might be an interesting research step, but like I'm not seeing news from this that it's about to flip the table. It seems interesting, this topological qubit system, that their potential for stability, their potential for scalability. It's a very interesting idea, but I'm holding it with modest skepticism for now. There's a little while back that some people came out with a room temperature superconductor, and then it turned out to be much less true than they said, and there's a lot of caveats, and that's kind of how I'm viewing the Majorana 1 chip. How do entangled pairs work in circuits in a physical sense? That is a good question. So I've said there's a lot of topologies, and also I'm not a quantum physicist. So how the entanglement works, I'm not 100% sure. I know on the existing topologies, they have to swap the qubits around until they're next to each other, and then they simultaneously expose them to a stimulus, and these are now entangled, and we can see that these qubits demonstrate that entangled behavior. At like the fundamental level of how does entanglement or why does entanglement work, I think that's still kind of an unopened question. But at the same time, I'm not a quantum physicist. But it's so yeah, that was a complicated way of me saying I really don't know. I'm a AI programmer. I'm a quantum computer programmer, so I don't have a lot of that. Yeah. All right. After Aomine's question, I'm going to shut it down. I'm going to do some research, but I'll be checking Discord throughout the day. But I'll go ahead and let Aomine finish typing. Yeah, Aomine, I just really don't know. That's a thing that I've allowed myself to be happily abstracted from. There's a lot of stuff happening with Josephson junctions and microwave pulses. You would, I bet that there's some resources online that can explain a little bit how that works, but I am not on the quantum hardware side. All right, guys. Hey, thanks for coming out. Looking forward to seeing you at 1 o'clock, and have a good day.